Hi guys, we're going to have a little look at anti-differentiation with partial fractions today. This is a very interesting and powerful technique to use when you've got algebraic fractions to worry about when you're doing anti-differentiation. So let's have a look at those and we'll see what we can find out. Partial fractions. Well, if we can decompose algebraic fractions into their simpler constituent parts or fractions, it becomes much easier to anti-differentiate them. And I'll show you what I mean. To create these partial fractions, we use the following rules. Now, we've got to watch this and get it off to a fine art, guys. Before proceeding with partial fractions, we check that the degree of the denominator is greater than the degree of the numerator. If not, and this is the biggest mistake that students make, they just don't seem to get this, please get this. If not, you must divide the denominator into the numerator first before proceeding with any partial fractions whatsoever. Now, do you see this? The degree of this numerator is 3, the degree of the denominator is 2. Therefore, the degree of the numerator is not less than the degree of the denominator, therefore you must divide the denominator into the numerator first. That is an improper algebraic fraction, and we have to fix that. So yes, you do a long division of the denominator into the numerator, and you get this as a result, and of course you continue on until you get your remainder. The degree of the remainder is less than the degree of what you're dividing by. That's where you stop. That's degree 1, that's degree 2, that's your signal to stop at that point. That's your remainder. So this over this gives the result that we got for the division plus the remainder x plus 1 over x squared minus 4. That's the very first thing that you've got to get from these partial fraction beasties, okay? Check that the degree of the numerator is less than the degree of the denominator. If it isn't, even if it's the same degree, you must divide. You must. Okay, second point. Before proceeding with partial fractions, we look at the denominator, and if necessary, we factorize the denominator. If possible, we factorize the denominator into whole number linear factors before proceeding. Now, you see this example we used before. We got this. Now, you see that quadratic there? That is factorizable. That is reducible into 2 linear factors. That's what we do, and there it is there, okay? If that was x squared plus 4, that would be irreducible. You wouldn't be able to do anything with it. But if you can complete the square or do something with it so you can convert it into 2 linear factors, you must do that, okay? That's the next thing, okay? Right, what else is on the agenda? When writing partial fractions, the degree of the numerator is always written as being 1 less than the degree of the denominator. So if you have this here, this one here, right? Now, you take the individual components of the denominator and you write them in a partial fraction manner such that the degree of the numerator, a is just a constant, which you could write that, if you like, as a times x to the naught. Okay, that's degree 1 less than x to the 1, which has a degree of 1. So that's what you would do there. So that's 1 less degree. That's a over x minus 2 plus b over x plus 2. Okay, that's what you would write. If you had an irreducible thing here, such as x squared plus 4, then this would be ax plus b. You phase it down by 1 at a time. Be ax plus b. If it was x cubed plus 1, for example, or something that you couldn't reduce, some cubic that you couldn't reduce down here, it'd be ax squared plus bx plus c up here. That's how you phase them down and write the numerator in that form, where it's 1 degree less, but it phases down 1 term at a time until you get to a constant. Okay, you're getting that? That's what you've got to do. Now, okay, so what's this? Take another example where the denominator cannot be completely resolved into linear factors. That's what I was just saying before. So the degree of the denominator is 3, the degree of the numerator is 2. That's okay, so we don't have to do any dividing, but this one's irreducible, okay? This one, that's okay, that one there. So you would say this, I've taken out just 2 as a factor out of this one here. So this would be You see that? See that there? Look. That irreducible quadratic, the numerator term is 1 degree less, but it's ax plus b, phasing down 1 degree at a time till you get to a constant. And then this one here is just c over x plus 3. That's 1 degree less than the x term here on the denominator. Yeah, that's what you do. Right, now repeated linear factors must be phased out one at a time. So this one here, if I have, that's what I call a repeated cubic repeated linear factor. So that becomes a over this one cubed plus b over the same thing squared plus c over the thing to the 1 till you get down to degree 1. That's how you handle repeated linear factors, okay? Now this one's only for illustrative purposes only. You don't have to do this. It's too hard, okay? But that's how you do them. That's how you do them, okay? Now you might have to do a quadratic repeated linear factor, but they won't ask you to do a cubic one. It would just be too much trouble. Okay, right, armed with that information, let's launch into them and see what we can do. Okay, so what's this? For each of the following rational expressions, we have to express them as partial fractions, and then we have to anti-differentiate the result. There's two of them there. Righto, A today, hooray. We've got this one. Now, okay, the first thing you look at is the degree of the numerator and the degree of the denominator. That's okay. Degree 1, degree 2. When you multiply that out, it'll be a quadratic of degree 2. So we don't have to do any dividing of the denominator into the numerator. We just have to partial fractionate it straight off. Yes, that's what it is. Now, okay, now look at this. I've multiplied both sides by the whole of the denominator, okay? And I get this. X plus 7 equals this plus this. Now, there is a very, very marvellous strategic little trick you can do with this. If you are picky in the way you pick, you don't have to multiply all this out and then equate coefficients. There's a much more strategic way to do this with these kind of ones here. Now, if I pick x as 3, that'll make that term go right down to nothing, won't it? And I'll just be left with a b term and something over here, which will enable me very quickly to solve for b. Then for the second trick, I'm going to let x equal minus 2, which means this term completely goes away, leaving me with just an a term and something over here, which means I can very quickly work out a. So that's really, really nifty, okay? When these terms are of the same degree, this x term is degree 1, this x term is degree 1, you can do it that way. When you have the repeated linear factor ones, that doesn't work so well. You might have to basically multiply all this whole right-hand side out here and then start equating coefficients. But for the vast majority of cases, this technique that I've given you works a treat. So I'll show you. Have a look. Subbing x equals 3, I get 10 equals just 5b, because this term is gone. And that's going to be 3 plus 2 is 5b, therefore b equals 2. I know, it is marvellous. So now we're going to substitute x as minus 2 into this beast, and we get 5 equals, that'll be minus 5a, won't it? Therefore a is minus 1. Easy as. Now we've got our partial fraction. One little caution here, I always, once I've worked out the partial fraction, a is minus 1, b is 2, I always actually recombine it on a scrap of paper or just in my head if I can, to make sure it actually works out to be that, so that I haven't made a mistake. Then I can proceed with really terrific, full confidence and basically hit it with the integration, which is easy now. See, look, how easy is that? They're just loggy ones, right? That's why you do these partial fractions. So, here it comes. Here comes the whole thing now. That's, we've got this one, plus this one from up here and up here. That's what we've got now. So that just becomes very, very easy. That's minus log of the modulus of x plus 2 base e, plus 2 times the log of modulus of x minus 3 plus c. Don't forget the c. Now, if you like, you can get all fancy and start using your log laws to make that look a bit prettier, but that is perfectly fine like it is like that. Unless they ask you for a specific form of the answer, that answer's fine. But I've just gone all a bit fancy and crazy with the log laws. That's the log of modulus of x minus 3 squared over the log, or over x plus 2. Yeah, because it's a minus, which means this one divided by the x plus 2 one. Okay, got it? Good, good, good. Let's go. B. Okay, what's the degree of the numerator? 1. What's the degree of the denominator? 2. Good. Don't have to divide denominator into numerator, it's just that. Okay, same technique. Multiplying both sides by the denominator, you get that. Now, what values of x am I going to pick, guys? You should know by now, based on the previous example. I'm going to pick x is minus 1, and then I'm going to pick x is plus 4. Look, this is what you get, and that's what you get, and then what you do the same thing with the x is 4, and you get that, therefore a is 1. I know, it's just fantastic. So that's what you get for your partial fractions. Then you've got to do the integration now, the anti-differentiation, and that'll be as easy as, there it is, you got that, and that loggy once again, guys, loggy once again. So it's going to be that. That's perfectly fine, that answer. Don't forget the C for you and me, and then if you want to get all fancy and combine it, you can do it like that. Yeah, but don't forget these modular signs. If you forget those modular signs, you're wrong. That's W-R-O-N-G in capitals with an exclamation mark and 3 asterisks after it. You are wrong. So please don't do that. Please don't do that. They're absolutely dynamite on it, the examiners. You must have the modular sign in. End of rant. Okay, what's this? What are these things? I don't think they're any problem for us. Let's do A today. Hooray. This looks like, yes. See, look, this you can turn that into linear factors, can't you? Difference of 2 squares. So it's basically that. Now, we can just partial fractionate that like that. Multiply through by the denominator, you get that. And now, what values of x am I going to choose, guys? To make this term go away, I'm going to make x minus 1. Then I'm going to make this term go away, I'm going to make x 1. So that's what you do. Get that, and you do that with x is 1, and you get that, and that's what you get. Now there's my partial fractions now. Now all I've got to do is integrate. Being very careful with this one. That's a minus x, right? That's going to get you, yes, minus the log of modulus 1 minus x, because there's a chain rule. Little operation has to happen in there because of the minus x, right? And the other one's fine, no dangers in that one. And now if you want to get all fancy, you can fix it up a little bit more and you'll get that. Okay, but this answer's perfectly fine as it is. Alright? Good show. Now this one here is a little bit more tricky because look. What's the degree of this? 2. What's the degree of this? 2. Oh, phew. That means we have to divide this into this before we do any partial fractions at all, guys. So that's going to be a bit of a pill. It makes you ill. And it won't give us a thrill, but we better keep going and do it. Okay, so NB. The degree of the numerator is 2, the degree of the denominator is 2. Oh, phew. So because the degree of the numerator is not less than the degree of the denominator, we must divide the denominator into the numerator first before we do any, even considering any partial fractions, guys. So let's do it. Come on. Swallow that bitter pill and we'll see what we get. Yes, 1 time, and then you multiply that thing by 1. Now you subtract and you get that thing. Now that's as far as we need to go, because the degree of that is 1, the degree of the thing we're dividing by is 2, so that there is our remainder. No need to go any further, guys. So therefore we've got this thing is equal to 1, which is what we got when we divided, plus the remainder, which is here, over the thing we're dividing by. Now we can proceed by getting partial fractions for this, and then proceed as normal. Okay, so we've got, what have we got? We've got the integral, or the antiderivative of 1, which is this term here, plus this thing here. Okay, now let's better go over the screen. Right, that's what we had. Now that's going to be that the antiderivative of 1 with respect to x is x, plus this beastly looking thing here we're going to have to partial fractionate now, plus c, don't forget the c. Now here comes the partial fraction side of it. So yes, look, that's just normal partial fractions, like I've just showed you in the previous few examples. Multiply through by the denominator, you get that. Picking x is minus 1, and then x is minus 4. Yes, 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 and there's our thingo from the partial fraction. Yeah, okay, they're loggy ones, right? They're loggy ones. So it'll be 3 times the log of the modulus of this, minus 2 times the log of the modulus of this thing. There it is. Now, I think I got all fancy with this. You don't have to, that's fine. It's fine just like that. Just like that, unless they ask you for a specific form of the answer. Yes, that's this term with the 3 stuck up as an exponent, then dividing by that term with the 2 put in there as an exponent. So therefore the answer of the whole thing is the x from up here, plus the answer to this thing, which turned out to be that, plus c, don't forget the c. How you going? I know, it's a bit boring, but look, it's very powerful. You can do it, and you can get it right too. So don't worry, just do a bit of practice. You'll get really good at it. Now, I think I've got 2 more for you. Well, we have to divide that one for sure, denominator into numerator. Yeah, the degree of the denominator is not less than the degree of the numerator, is not less than the degree of the denominator, therefore we've got to divide denominator into numerator first before we even think about partial fractions, right? Let's do it. That goes x cubed times, multiply x cubed by this thing now. We get that, don't we? Now we've got to subtract. Be careful, subtracting negatives, they come out as positive. Yes? Now, it looks like we've got to go 1 again, because the degree of this is still more than the degree of that. So that'll be x. Yeah, x. Now x times x squared minus 1 gets us x cubed minus x. Now subtract. Again, you'll get x plus 2. That's our true remainder, because the degree of that is less than the degree of this, so we can stop now. So now we know that x to the 5 plus 2 over x squared minus 1 is x cubed plus x plus our remainder over what we're dividing by, our divisor. Okay, now that's looking considerably easy to integrate, guys. That's going to be a quarter of x to the 4, that's going to be a half of x squared, and this is going to be, we're going to have to fiddle and partial fractionate this, but that is reducible into x minus 1, x plus 1, isn't it? Yeah? That's what we get. That's what we get from there, as I was saying. Now we've got to do some surgery on this. Partial fractionate it, as usual. So yes, don't forget the c. Now, yes, this thing here is a over x minus 1 plus b over x plus 1. Let's do that. So multiplying through by the denominator, we get that. Now, the values of x I'm going to pick are going to be minus 1 to get rid of this term, and then plus 1 to get rid of that term. That's what we do. That's what we get. Yes, and that's what we do, and that's what we get. Well, cooking along beautifully. So therefore we get that, don't we? Is that A? Yeah, where's A gone? Yes, A was over x minus 1. That's right. So A is 3 over 2. B was minus a half. That's right. Loggy ones again, guys, when you integrate those. That's what we're going to do when we get the integral of that. So that's going to be 3 over 2 times the log of the modulus of that beastie minus a half of the log, what's that thing? The log of the modulus of this beastie. Now, if you want to get all exponent happy, fiddle with it, you can, but you can leave it like this as well. That's perfectly fine. In fact, I actually advise not to go fiddling with things. That's close enough, good enough. If you fiddle with it and get it wrong, you actually lose your answer mark. So don't get all, fancy and, end up in the algebra ditch and lose your marks. But I've done that. I've done it anyway, okay, just to show you how to do it. Yes, that's there. That's there. And then you can even do a further term where you've got the log of this divided by that. There it is, guys. Now, okay, I think we're ready for our final answer after all that mucking around. And we get that. Don't forget the C. Don't forget the C. Or, actually, if they just ask you for an antiderivative, an antiderivative, you can leave out the C. But if they ask you for the antiderivative, you better put that C in, otherwise they're dynamite. They'll take your mark off you. You will lose the answer mark, okay? I know, it's very serious, so don't do it. Now, oh yes, a last hurrah! We've got a repeated linear factor one, okay? Look. That's linear factor squared. So the rule, do you remember what I said for the rule for this? That was the last thing I showed you in all those rules of partial fraction. So first of all, you say, look, the degree of this is 1, the degree of that is 2, so I don't have to do any dividing, thank goodness. But I do have to do the phasing down of the linear factors. So See that thing there? That's equal to, the rule says that's equal to a over the whole thing squared, and you phase it down by one power at a time till you just get a linear version, right? So b over x plus 2. If that happened to be x cubed there, it'd be a over x plus 2 all cubed plus b over x plus 2 all squared plus c over x plus 2. But thank goodness it isn't that, it's just this one, so we can stop there. Yeah? Alright, so now, this is a case where where my beautiful technique doesn't work so well, because we've just got an a term here and a b into x plus 2. So we do have to actually multiply this whole thing out now, which isn't too much trouble in this case, and equate coefficients. Remember I said earlier that when you have repeated linear factors, that marvellous strategic choosing of x technique doesn't work so well, so you've got to use the traditional. There it goes, bx plus a plus 2b, which is not really a big problem anyway, it's pretty easy. But for some of them it gets pretty, a bit gurky. That if it was a cubic linear factor, it would be a much more gurky than that, let me tell you. But it isn't, thank goodness. So, okay, so what are we saying? Therefore, 3x must be bx, and we're saying that a plus 2b must be equal to 1. So that, well, b is 3 for a start. Plug b is 3 into equation 2, and what do we get? 1 equals a plus 2 times 3, which is 6, therefore a must be 1 minus 6 would be minus 5 to keep us alive and help us to thrive. And what have we got now? Goodness, what's all this? Yes, that looks good. That looks good. Now, that was the a term, which turned out to be minus 5, and that's the b term, which turned out to be 3. Yeah, that's good. But this these two separate integrals here, I've written them as two separate integrals because they are two separate processes to get the results, so I'll have to consider them separately. This one's nice and easy, that's just 3 times log base c of the modulus of x plus 2, but this customer here, I'm going to have to get Mr. U to ride in on his white Charger and come to our rescue. Hello, Mr. U, are you there? Come in, Mr. U. Oh, I think he's there. So for the first term there, ah, you are there. Good for you, Mr. U. So u is x plus 2, and therefore du dx equals 1, and therefore du equals dx. Now we can change the whole thing over to u. Oh, isn't he magnificent? Mr. U, he's saved us. He's saved us. So now for what we've got, we've basically got, that's u to the minus 2, which should be minus 1 times u to the minus 1, multiplied by minus 5 out the front, which will get us minus 5 over u plus c. Don't forget the c. Now we're out of the integral monster can't get us anymore, so we're going to substitute back for u. There it is. Goodness, it's 5 over x plus 2, because u was x plus 2 plus c. Well, we've done the first term, now we're going to do the second term now. Fortunately, that's very easy. As I said, it's just 3 times log of the modulus of, what did I say? 3 times log of the modulus of x plus 2 base e. So therefore, the whole entire answer is there. Is that it? That's it. That's it, guys. That's it. Alright, we're done. And now we can get out of here, and you can go and do some practice. And you're a star, and you'll go far, huzzah, and hurrah, and we'll see you in the next exciting instalment of the Land of Anti-Differentiation. So we'll see you. Bye-bye.